discuss about maximum shear force and maximum bending moment in beam supporting uniformly distributed loads. Okay, if UDL is rolling on the beam from one end to other end, then there are two possibilities. One is uniformly distributed load is longer than the span, and other cases uniformly distributed load is shorter than the span. The longer than the span, you can imagine one train moving on the track. Okay, that is longer than the span, and shorter than the span, the train resting on the track, that is shorter than the span. So depending upon the length of the load and span, the maximum shear and bending moment in beam supporting UDL will change. So we will see in detail how it is in the case of UDL longer than the span and how it is in the case of UDL shorter than the span. So first we will see UDL longer than the span. What we have to do, let us assume one simply supported beam AB of length L. Okay, section is here located at a distance of x from A, and this is L minus x. Okay, next the maximum negative shear can be achieved when the head of the load is at the section. Okay, here I have written C but marked as X. Consider it as a X. Okay, now section is here. When it is moving from left to right, this is the first position. So this is head and this is tail. Okay, so when what you have to do in the case of negative shear force, when the head of the load is at the section, so you have to start the load from the section. Head of the load is at the section, so it is moving from here to whatever that length, that is negative shear force. Next you have to consider positive shear force. What is that? Positive shear can be obtained when the tail of the load is at the section. So you have to start from the tail, when the tail of the load is at the section, that is positive shear force. And what is bending moment? Bending moment is the load will cover the entire span. Here it is longer than the span, so it is more than this AB. Okay, so you have to extend beyond the supports. So that is for bending moment. So I have shown here negative shear force, first diagram, positive shear force, this one, and maximum bending moment. Okay, corresponding ILD I have drawn. This is the basic ILD diagram. For shear force at the section it will have two values, and at the support it is 0. Similarly for bending moment, at the support 0 and at the section it has maximum value. Okay, once if it is done, next you have to find ILD for shear force and bending moment. So find these points. What are these ordinates? Here ordinates. Here ordinates. Once if it is drawn, then you can find what is maximum negative shear force, what is maximum positive shear force, and what is maximum bending moment. What is positive shear force or shear force? The shear force can be calculated by multiplying this intensity of the load into the area of the influence line diagram covered by that load. Suppose now you are calculating negative shear force. What is that? Intensity. Intensity is W per unit length into area of the influence line diagram covered by the load. So for the negative shear force, this is the area covered by this load. Okay, so that is triangle. So intensity into half into base into this height. Okay, that is negative shear force. What is positive shear force? That is intensity into area of the influence line covered by the load. So this is the area. So intensity into half into base into this height, that is positive shear force. Next, what is maximum bending moment? It is given by the load intensity multiplied by the area of the influence line covered. So this is full area. You can consider it as one triangle, or you can consider it as separate also, no problem. For easy it is, we'll consider it as one triangle. So half into base into this is the height. So once if you get this is the way to calculate what is maximum shear force, bending moment, and both positive and negative shear force and bending moment. This is for the case UDL longer than the span. Next we will see UDL shorter than the span. So here also let us assume one simply supported beam AB of length L, and this is section which is located at a distance of x from A. So this is L minus x. Okay, intensity is W per unit length. So when the length of the UDL is shorter than the span, maximum negative shear can be achieved when the head of the load is at the section. Same thing like last case, UDL shorter than the span, like that only here. Negative shear is induced when the head of the load is at the section. Here it is shorter than the span, so it is only till here, that distance. Okay, so I have marked here negative shear force. Then what is positive shear force? Maximum positive shear can be obtained when the tail of the load is at the section. So you have to start with the tail. So tail of the load is at the sections for some distance. Okay, next the shear force is computed by the load intensity multiplied by the area of the influence line covered by that. Means same thing like last class, shear for like last problem, there is no difference in the shear force, only bending moment there is some difference. Okay, so this is what I consider negative shear force, shorter than the span, only this much length, and this is positive shear force, smaller than the span, so this distance. Okay, and then I have drawn this ILD for shear force, that is same thing diagram. At the section you will have two values, left section minus, right side plus. Okay, now this is total shear force is calculated by intensity into area of the ILD covered by that load. Now this is the load position, so it covers the area, only this area, not full. Okay, so this area, and positive shear force intensity into area covered by the ILD from the load. Okay, so this portion. Okay, so now what is this? This is trapezoidal, so you have to use that area, intensity into area of this, and for positive shear force, intensity into area of this. Okay, now bending moment, here there is some difference. How it is calculated? Maximum bending moment is also here, also it is given by the load into intensity, intensity into the area of the ILD covered by the load, that is same. The maximum bending moment is given by the load intensity multiplied by the area of the influence line covered, so intensity into this area. But in this case the load should be placed in such a way that the section divides it in the same proportion as it divides the span. Okay, this you have to remember here. The load should be placed in such a way that the section divides it in the same proportion as it divides the span. Okay, so I have drawn like this. We don't know now what is the distance, this is just example I have given. So this distance, it is only shorter than the span, so this distance, so corresponding bending moment you have to calculate. How you can calculate this distance? Either Cx or xt, both distance you have to calculate. How you can calculate? You can use either Ax divided by xb is equal to Cx divided by xd. Okay, that is one assumption. Or Cx divided by Ax equal to Cd divided by AB. Whatever. Next case, or Cd, this is next case, CD divided by AB is equal to XD divided by XB. Any one combination you can take. So using this equation, using this is the just graphical representation. All you know this, you have studied in mathematics. Okay, apply that concept and find these two distance. Once if you get distance, you can calculate this distance. Okay, so this is the basic diagram you have to draw for both the cases, UDL longer than the span, also shorter than the span also. Once if you know this, then you can solve any type of problem. Okay, so I'll just summarize. In the case of longer than the span, what you will have triangle area of that ILD is triangle, both the shear force positive and negative, and even for the bending moment also. But in the case of UDL shorter than the span, what happens, that is the area is different you get, because only half portion, that load covers only the half portion, so it looks like the trapezoidal, both shear force as well as bending moment. Okay, in the UDL longer than the span and UDL shorter than the span, positive and negative shear force same, but only the difference is in the bending moment. What you have to think, you have to assume the way that the load should be placed in such a way that the section divides it in the same proportion as it divides the span. So this you remember, then you can solve the problem. Okay, and this any one of this formula you remember, so you can find what is this distance. Okay, next class we'll see how to solve the problem. Okay, thank you.